In this lecture, we'll be sweeping up almost the entire story of neurophysiology. We're going to start off by making a simple sketch of a neuron, dendrites, cell body or soma, axon, covered by these little bubbles, myelin sheaths, and the axon terminal. In order to begin the story, we do have to start off with what we'd probably consider to be the first part of the neuron. So I'm going to draw a yellow box, and I know it's hard to see, but I didn't want to make a big deal out of it. We covered this in the last video, so I'm going to be covering it quickly. Dendrites, soma, and axon hillock, that first part of the axon, all are responsible for this type of neurophysiology that we're going to be discussing over here on the left side of the page. And so we're going to redraw receptors that we drew in the prior video just as a simple review. As is our wont, in orange we have the plasma membrane, and we have embedded two different receptor channels in this plasma membrane. The first one we're going to be discussing is going to be binding the neurotransmitter GABA, gamma-aminobutyric acid. There it goes. We have a little molecule of the neurotransmitter GABA, which is attached to the binding site of this receptor channel. And as a result, we have chloride ions, which are negatively charged, which enter through this channel because that is the direction of their diffusion gradient. And of course, in that case, you're bringing more negativity into the cell. The next one down the line, we're going to have acetylcholine binding to the binding site, and in this case, it is permeable to sodium ions, and so these positively charged sodium ions will be entering the cell, influxing into the cell, bringing positive charges into the cell. They gather, as you can see, very close to that inside layer, surface of the plasma membrane, and therefore they actually displace the negative charges. Remember that you have negatively charged phosphates and negatively charged proteins that usually line up along the inside of the cell, but in this case, when sodium ions come along, and there's so many of them, that they oftentimes will kind of line up very temporarily and displace those negative charges, as you see here. So let us go ahead and label a few things. Of course, both of the structures that we're looking at here are called receptor channels. In this point, they're both open because they are both binding a neurotransmitter. The GABA receptor channel allows for the influx of chloride ions because it's permeable to chloride ions. And the acetylcholine sensitive receptor channel allows for the influx of sodium ions, sodium influx. And we're going to go further. We did discuss this in the last video, so this is just a review. When we have positively charged ions, such as sodium ions, entering into the cell, it's called excitation. When we have negatively charged ions, such as chloride ions, influxing into the cell, it's called inhibition. Now, both of these are examples of local potentials, also called graded potentials. Local potentials or graded potentials only occur along the dendrites, soma, and along the axon hillock. They do not allow for that to occur down the length of the axon. The axon experiences an action potential, which has an all or none, very dramatic situation. But local potentials or graded potentials tend to be decremental. They tend to decay over time. They tend to be more graded. They tend to be more gradations of a signal. In other words, they can be larger or smaller. So we're going to explore that next. We're going to go further, and we're going to call an inhibition a hyperpolarization. And an excitation we're going to call a depolarization. It's basically different terms for the same exact thing. But what does that actually mean? In order to explore the concept of depolarization and hyperpolarization, we need to stick a little microelectrode directly into the cell body, and we need to measure the difference between what's happening inside of the cell versus the outside of the cell. And so that we're able to measure the potential for things to happen. So we're going to draw an XY axis, and on the x-axis we're going to write time in milliseconds, and on the y-axis we're going to write the word membrane potential. Membrane potential is a sophisticated term that actually involves a lot of different definitions and processes, but for now I think it's important for us just to recall that there's the potential for things to flux into a cell or out of a cell, what we're really kind of considering is the potential for sodium ions to cross into an area where there is a perceived negativity with all those negatively charged structures lining up along the inside of the cell membrane. So I think that's kind of enough for you to conceptualize the idea of a membrane potential. The membrane potential is the idea that the inside of the cell is perceived negatively because it has these negative charges lining up, and therefore the positive charges line up on the outside, and they sort of influence each other, and there's this polarity across the membrane. The inside of the membrane is negative, the outside of the membrane is positive, and therefore there's this potential for sodium ions to influx into a region that appears to be more negative. So although that explanation is rather unsophisticated, hopefully it's enough to convince you that we will put 0 at the top of this and we'll put minus 70 way down at the bottom, because this is actually where we kind of start our story. Our resting membrane potential, our RMP, is going to be held at minus 70 millivolts. So our membrane potential is typically held in natural circumstances, no events occurring at all, at minus 70 millivolts, with, of course, variability between cells, but typically we use minus 70 as a hypothetical number. Well, the resting membrane potential is just what it sounds like. It's resting. However, there are events that can occur that can either make the membrane potential go down or the membrane potential to go up. When we cause the membrane potential to go down, it's called a hyperpolarization, which we actually wrote this term below. And when we cause the membrane potential to go up, it's called a depolarization. The word hyper means more than. So when we cause a hyperpolarization, we are increasing the polarity of the membrane. We already had a membrane that was quite a distance from 0, and we're increasing it even further from, say, minus 70 down to minus 75. When we depolarize, we're taking away some of the polarity. Instead of this split of 70 millivolts between the outside and the inside of the membrane, now we're taking it up to minus 65, for example. So let's go ahead and skip down below where we already wrote these terms, actually, the term hyperpolarization and depolarization, and we're going to redraw the little dip and the little bump. And now we're going to be a little more specific about how this actually occurs. A hyperpolarization that we've studied so far is caused by the influx of chloride ions into the cell. Negatively charged ions entering the cell causes a slight dip in the membrane potential, whereas sodium ions influxing into the cell causes a slight depolarization, a slight rise in the membrane potential. But there actually is one other way that hyperpolarizations occur that we study, and that is through the efflux of potassium ions. If you think about it, potassium ions are going to be positively charged and they're higher concentration inside of the cell, so when they efflux, they actually cause the inside of the cell to become a little bit more negative. So chloride influx or potassium efflux, either one would cause a hyperpolarization, and a depolarization, as far as we study, is only caused by sodium ion influx. Now, the graded potential of the local potential happened at the dendrite, soma, and axon hillock. But now we're going to take a closer look at the axon hillock by itself and take a look at exactly what is happening there. So what we're going to do is we're going to redraw just that very last part of the soma, or the cell body. And then we're going to draw the axon hillock, which is the very first part of the axon. And we're going to stick our microelectrode in there so that we can measure the electrical potentials that are happening in that area. Now, I need to redirect your attention to the fact that at the dendrite, for example, or at the soma, you might have, for example, an influx of sodium ions. This is called a graded potential, and it oftentimes decays, but at times there's enough of an influx of those sodium ions that they actually make their way all the way along the cell body and into the axon hillock. And you can see then that what's going to happen is, if we're measuring just at the axon hillock, you see the microelectrode is set up in there. We have our membrane potential measured in millivolts. We set up our minus 0 and our minus 70, and we also add another dotted line here. This is going to be our threshold line. The threshold line is usually 15 to 20 millivolts higher than the resting membrane potential, and it allows for exciting things to happen, which we're going to detail here. So first of all, let's draw our resting membrane potential at minus 70. And again, we're going to remind you that the local potential happening more proximally up the neuron, this is the listening part of the neuron, had an influx of sodium ions, which caused a depolarization. In this case, the influx of sodium ions did not actually reach threshold. And so that depolarization that occurred, it just bumped up a little bit and you went right back to resting membrane potential. However, let's say that there was enough of a signal, there was enough of a bump up of sodium ions that you actually reached threshold. Now, we're going to talk specifically about what happens here, but what I can say just sort of conceptually is that when you reach threshold, there's a huge influx of sodium ions and a massive depolarization as a result. Look at this, I forgot to label my x-axis. You always got to label your axes, people. So time in milliseconds on the x-axis. We're going to go ahead and label these. On the left, we have a sub-threshold depolarization. It did not quite reach threshold and nothing exciting really happened. But when we had enough of an influx of sodium ions and enough of a signal entering into the Axon Hillock, we had the initiation of an action potential because that graded potential allowed us to reach threshold. So we'll talk about what happens next with that. But before we do, I want to detail kind of a specific example of something that can happen at the Axon Hillock, but a really interesting example, and it happens all the time in the nervous system. So I hope that you get this point here. We have inserted into the Axon Hillock a GABA-sensitive receptor channel, which when GABA binds to it, of course, allows for the influx of these negatively charged chloride ions. Now, we have this sodium influx, these positively charged ions, way up at the dendrite, the soma, kind of further away. So this inhibitory connection here with the chloride ion influx and the GABA channel, this allows for a very specific type of inhibition right at the source. The primary way that our nervous system works is actually by diminishing unnecessary signals, and this is exactly how it is done. There could be a lot of fluff happening, a lot of erroneous signals, a lot of things we don't really need to pay attention to out at the dendrites. They might be receiving tons of information, and in fact they do all the time. They're receiving all kinds of information. Not all of it is relevant. So let us say that instead of simply sending signal after signal after signal down the length of the axon, let's say that we go ahead and inhibit some of these things. And it looks like this. We have a hyperpolarization, which is represented with a slight dip in the membrane potential. I'm drawing it in purple because it's caused by the influx of chloride ions through this GABA-sensitive channel. But it's followed by a pretty significant bump up in pink through the influx of sodium ions. It's possible that these sodium ions might have been enough to actually reach threshold, but since we made sure to inhibit the membrane potential ahead of time, we made sure that we actually didn't reach threshold because, again, not everything that hits the dendrites is a signal that is relevant enough to cause an action potential. So this is called the inhibition of signal, and it's done all the time, and it's usually through GABA-sensitive receptors right there at the axon hillock, shown just as we showed it here. If you've ever previously had a lesson in neurophysiology, it's likely that you studied the action potential a bit, and you probably looked at it something like this. You have these myelin sheaths, you have an axon, and you have this thing that sort of looks like an EKG in the heart, and it sort of jumps down the length of the axon all the way to those axon terminals. So let's study exactly what this is. Of course, we have to start at the proteins that are involved with this. There's always proteins. Remember, there's always proteins. The protein in this case is going to be a voltage-gated channel. So the voltage-gated channels have little airplane wings kind of sticking out the sides of them. You'll see that it is a channel. So I'll draw one that is closed, and then I'll draw one that is open. And you'll see the difference in those wings, those little airplane wings. We actually call it a paddle model, sort of like paddles sticking out. I've always thought it looked like airplane wings, but according to the literature, it is paddles that stick out straight to the side or they pull up. Now, when they are pulled up, the channel opens. Now, this is happening only along the axon, but of course, it's still the same plasma membrane as happens along the rest of the cell. So we portray it in orange, and then we're going to go ahead and draw a large number of sodium ions lined up on the left-hand side there, and then a smaller number lined up along the right side. This is important. So on the left side, we go ahead and draw our negatively charged phosphates and proteins, and we're not going to draw them next to the open channel. So what's going to happen is we're going to bring in a whole population of sodium ions that have come from the direction of the Axon Hillock. And at the Axon Hillock, we had this huge influx of sodium ions, which we did portray down below, but it happens this way. These could have also come, for example, from the soma or from the dendrite if there was a huge influx of them. And what happens is there's such a large number of sodium ions inside of the cell all of a sudden, which remember, they're usually considered in higher proportion outside of the cell. There's such a huge proportion of them inside of the cell that they actually displace all of those negatively charged structures. And there's some amount of negative charges, like the chloride ions, that line up outside of the cell. And so this is a voltage-gated sodium channel. In its closed state, nothing is allowed through. In its open state, it allows sodium ions to flux, and in this case, of course, they are going to influx. We still have that gradient where the sodium ions are going to flux into a region which is perceived as negatively charged, even though it is very briefly polarized in a different direction. So through the voltage-gated sodium channel, the actual change in the voltage of the channel, of the voltage of the membrane itself, is going to cause the opening of the channel. It turns out in those little airplane wings, there are positively charged. Do you remember that proteins are made of amino acids? And it turns out that there's positively charged amino acids in those little airplane wings. And so that actually forces them upwards when we have a lot of positive energy inside of the cell. So a voltage-gated channel allows sodium influx, and as you can see, this causes a huge, massive influx, which is called the depolarizing phase of the action potential. Next, we have the repolarization of the membrane potential, which actually tends to be caused by the closure of those sodium channels, or the inactivation of the sodium channels, I should say, which we're not showing in detail here, but basically we can just view it as a closure of the channels. And then lastly, we have potassium efflux, which is going to be a hyperpolarization. Remember that we showed that potassium efflux can also cause hyperpolarization, and that is what we see here. And so let's go ahead and draw how that happens. This is going to be voltage-gated potassium channels in their open state and then in their closed state. It's going to be the same thing that causes those airplane wings to flap up. It's going to be positively charged amino acids in those little wings there that tend to flap up and away from an area where there's a huge, massive influx of sodium ions. And so these voltage-gated channels, in this case, this is a slight delay of about 2 milliseconds that allows the potassium channels to open. So voltage-gated sodium channels and voltage-gated potassium channels actually both open for the same reason, which is the sodium ion influx. It's just that the voltage-gated potassium channels, they have a little bit of a delay. They're called delayed rectifiers. And so you see the potassium efflux in this case, which causes a slight hyperpolarization, which causes the membrane potential to dip below the resting membrane potential for just a brief period of time, making the next signal much less likely. We're going to go ahead and draw just a small portion of this axon. We're going to really blow it up so we can see close up exactly what's happening. And so these sort of circled off squares that I'm drawing here are going to be the myelin sheaths. And we're going to draw both sides of the membrane. The axon has, of course, a plasma membrane on either side. And we're going to go ahead and put some voltage-gated channels in there, which it's a little bit difficult to draw all the details of a voltage-gated channel this small, but I'm going to go ahead and try to draw those little airplane wings. In this particular, what we call a myelin sheath gap or a node of Ranvier, we're going to draw voltage-gated channels that are open. And in the next gap, we're going to go ahead and draw voltage-gated channels that are closed. Again, this close up, you can't really see whether the wings are flapped up or down. So we're going to go ahead and draw our ion flux in the first gap and no ion flux in the second gap, which is indicating the channels either being open or closed. Okay, so we're going to bring our sodium ion, our depolarizing current into this first gap here. And so this would either be coming from the Axon Hillock or coming from the previous gap. And we're going to show sodium ion influx and then potassium ion efflux through these voltage-gated channels. And the depolarizing force from that first opening, the massive depolarization, those massive influx of sodium ions, is going to carry on down the length of the axon. And the next thing it's going to do is cause opening of these next voltage-gated channels. However, at this point, that depolarizing force has not yet reached those channels. So we just have a resting membrane potential, flat line. Doesn't reach threshold. But in this case, in the first gap, yes, we have a depolarization, a massive influx of sodium ions, followed by a massive efflux, well, not a massive, but a substantial efflux of potassium ions, which then allows a slight dip below resting membrane potential, and then eventually it recalibrates to our RMP, our resting membrane potential. And I tried to kind of draw this action potential trace a little bit spread out so that you could actually see the matching depolarization with the influx of sodium ions and the hyperpolarization with the efflux of our potassium ions. All right, to reiterate our entire story, we have graded potentials, either depolarizations or hyperpolarizations, just slight ones. You know, a proportional amount of influx would cause a greater amount of a bump or a greater amount of dip, either a hyperpolarization or a depolarization. This is going to be a graded potential or a local potential that commences typically at a dendrite or at a soma, which is where a signal is received. It's some kind of information, either from a neuron that's previous in line or from a mechanosensation, some kind of a touch or something like that. We then direct our attention to the axon hillock, the most special part of the neuron, where a number of different things are going to occur. There's going to be voltage-gated channels in this area, but there's also going to be chemically gated receptor channels in this area as well. And oftentimes those receptor channels will be inhibitory. Oftentimes they are GABA sensitive, and therefore they allow that influx of chloride, which in turn then causes a diminishment or the less likelihood that you're going to be passing on an unnecessary signal. We have this last opportunity to inhibit or stop a signal from making its way down an axon and causing more and more signals to be passed on if those signals don't actually need to be passed on. We have that ability. So the axon hillock is where the initiation of an action potential occurs. There are voltage-gated channels here, and then there are also chemically gated channels here. Lastly, we have what's called the propagation of an action potential, where we continue to pass on the signal from myelin sheath gap to myelin sheath gap to myelin sheath gap, and it continues on like that. Action potentials are all or nothing. Once they start at the axon hillock, they are always passed on in exactly the same way. The influx of sodium ions through voltage-gated sodium channels, followed by the efflux of potassium ions through voltage-gated potassium potassium channels, and both of these channel openings are caused by a reversal of the polarity of the membrane briefly as sodium ions, these positively charged sodium ions, kind of make their way down the length of the axon, ensuring the displacement of the negative charges along the interface of the membrane, and ensuring that the membrane potential continues to reach threshold, boom, 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 all the way down the length of the axon. Now, the next thing that's going to happen is that there's going to be a signal that is going to be crossing the synaptic cleft. But today, that is as far as we're going to go, so we're not going to quite get to the synapse yet, but we have this dispersal of electrical charge that's pretty dramatic that ends up affecting changes within each of the axon terminals that are at the end of this axon in turn.